Thank you. Thank you, everybody, for coming out tonight to the East Hampton Library to tonight's lecture, which is being co-presented by the Hamptons Observatory. And we'd like to give our appreciation to the observatory for giving us the opportunity to host this event. They have some wonderful, wonderful programs through the Hamptons Observatory. And I just would like to introduce Terry from the observatory to say a few words about our speaker tonight.
Thank you. Thank you. Thank you so much for hosting us. Well, I'm Terry Beanstalk. I'm president of we used to be the Montauk Observatory. I still say that, but Hamptons Observatory as we moved a little further west. So for those of you who know us, we've been around for over 20 years now. It's hard to believe. It goes by very fast. What we've tried to do when we set the group up was to promote science education for folks of all ages. And we really have done an incredible job of hosting some of the greatest experts in the world for our lecture series. And we try to do it year-round. So oddly enough, we find our attendance during the winter months actually is good or better than during the summer months because there's so much competition during the summer for people's time. And we've been doing this for, as I say, almost for over 20 years. We also have the ownership of the largest professional-grade telescope in Long Island. People don't know about it, but it's at the Ross School in an observatory. It's been there for several years, and it is a remarkable telescope that we have made available to anyone who wants to use it as we've done the lecture series. So let me tell you our philosophy. Everything we do is free. Not free to us, but free to the public. And that was our founding proposition, is that we didn't want to ever charge anything because we want people to come, we want to educate everyone, and we want to make it available to people of all ages and kids and teenagers and students, and that's what we've done. It's a challenge because, as I say, it may be free to you, but it's not free to us. So all I can say is hamptonsobservatory.org. Joining is free. Sign up. You'll get all the newsletters. You get access to all of the lectures we've done over the decades. They're on, I think, done on YouTube, right? On YouTube. And we make sure that we post everything as promptly as possible. But we also do other things. We do star parties. We do planetarium shows. We try to do it throughout the South Fork, everywhere from West Hampton to Montauk, up to Sag Harbor, and we try to rotate town by town so everyone gets something close to them. But obviously the sort of the central location for us is East Hampton because that's where our building is and our observatory at the Ross School. And the Ross School has been a fantastic partner of ours for many years. So I say that because although you can join for free and you don't have to do anything, we certainly welcome donations, sponsorships, and as important is participation. We've had most of our core group have been the same folks for 20 years, and we're aging out. Not me, but others. And we're trying to bring in other folks who are interested in astronomy especially to help strategize our future, because we're going through an inflection point in our group right now on what to do with the telescope, what to do going forward. COVID was an interesting experiment for us. First, we thought it was going to put us out of business because we couldn't do live events, so we did them by Zoom. And instead, we become internationally known as a result. And the lecturers we got, because everything was virtual, are literally from all over the world. They didn't have to happen to be out in the East End. We're fortunate. We have a lot of scientists. We have a lot of writers. We have a lot of folks who have great expertise that happen to have homes out here because they work in the city, they work at Columbia, they work at NYU, they work at the various universities on the island, Stony Brook. So coming out here was not a great chore, but by having virtual lectures, we're able to attract people from Poland and people from Denmark and lecturers from Paris. It's been remarkable, and we've expanded our horizons as a result. So that being said, there's nothing like live in-person presentations, so we went back as soon as we could. We try to do a lot of it as hybrid. So that's what we're doing. With that, I'm happy to talk tonight about Dr. Helfand, who's a remarkable scientist at Columbia University. He is, the information I have is incorrect, because it says he's been faculty member for 48 years, and he corrected me. It's now 49 years. Not in September, well, that's in 10 days. He served for nearly half the time as chair of the Department of Astronomy. He's the author of over 200 scientific publications and has mentored 23 PhD students, by the way, including, for those of you who attended the Neil deGrasse Tyson event, him. He's the one who brought him to Columbia. So when Neil said he's my mentor, he meant it. Most of his efforts have been teaching students who are non-science majors science, which is very important as well. He initiated the first change in Columbia's famed core curriculum in 50 years by introducing the course Frontiers of Science, now required for all first-year students. He is, in 2005, he joined an effort to create Canada's first independent nonprofit university, Quest University in Canada, where he served as President Vice-Chancellor from 2008 to 2015. He completed a 4-year term as President of the American Astronomical Society and is currently chair of the American Institute of Physics. His acclaimed first book, A Survival Guide to the Misinformation Age, is in the rear. You can buy it, and he'll be happy to autograph it. His current book is Universal Timekeeper, Reconstructing History Atom by Atom. And again, it's back there. You can buy it. He'll autograph it. And that's what he's going to be talking. Dr. Helfand, we welcome you. Thank you.
I guess I'll start two of these. I have poppy seeds. You have to take the poppy seed, and your challenge is to get it to the last person in the last row on your side. Now you might wonder why we're doing this. Because if you succeed, it means each of you will have held in your hand 15 million trillion atoms. This talk will have a lot of big numbers and small numbers, so we have to give you some visualization of this. So let's say the atom were the size of a marble. Here's a marble. So suppose atoms were that big. Well, then a trillion atoms, or a trillion marbles, would require a warehouse that's a New York City block, so say from Columbus to Central Park West, from 72nd to 73rd Street, 20 stories tall, packed with marbles. That would be a trillion. But I just told you the poppy seed, it's got 15 million trillion, which would require a warehouse covering the entire landmass of New York State, and you have to extend it to 30 stories tall. Needless to say, you don't interact with the world at the atomic level. Did we make it to the back there? They're getting there, they're getting there. So I hope this helps you visualize the scale on which we're going to talk about things. But of course, what's remarkable is that we have developed techniques to count individually each of those atoms, to sort them by type, and to inquire as to their internal states, which allows us to use them as hyper-accurate historians, timely historians at that, to reconstruct the history of humankind and the 13.8 billion years that came before humankind. So as they say, if the atom were the size of the marble, then it would be the poppy seed that ate Manhattan. It would be 20 kilometers tall. So that's, what, 100 times the height of those awful buildings on 57th Street. Now, you interact with matter at a slightly different level, the level of classifying things crudely as solids, liquids, and gases. The particles that make up solids and liquids and gases are not different because the particles themselves are different, but it's just how they're packed together. So if these are two particles, in the coffee cup and the ceramic and the silver spoon, the particles are touching each other, and they're locked rigidly in place. So the best they can do is vibrate like this, and that's what they do. Okay. So that's what the chair is doing now, that's what the molecules in your skin are doing now. In a liquid, when you pour the coffee from the coffee pot into the cup, of course it changes shape. And it changes shape because while the particles that make it up are still touching each other, they're broken free and they're now free to roll around each other. So they can move and change shape. Whereas the aroma that's coming off the coffee is in the form of a gas. And in a gas, the particles are not touching each other, they're far apart, and they interact by bouncing off each other like billiard balls off the floor and anything else. And in the air in this room, the particles are about this far apart. They're about 10 times farther apart than their diameter, which is why you can take your hand and go right through them, because there's not many of them there. So that's how you interact with matter. But what are these particles? Well, this is a subject that has puzzled philosophers for at least 2,500 years. And we don't know exactly who came up with this idea first. It could have been Kannada, who was an Indian sage from about 600 BC, or it could be from Leucippus and his very energetic student Democritus about 100 years later in ancient Greece. But if you take a piece of paper, you recognize this as a substance, and you tear it in half, then the piece of paper is smaller, but it's still a piece of paper. It has the same density, it has the same reflectance of light, probably tastes the same if you chew on it. And if you cut it in half again, you still have a piece that you recognize clearly as paper. And you can keep going, doing this, right? And you'll get smaller and smaller pieces of paper. And eventually, it's not crazy to think that you get to a point where you have the smallest piece of thing that was still paper, that still had the properties of paper. The Greeks called these atoms, or atomos. Now, in fact, Democritus and Leucippus lost out to Aristotle, who came about 100 years later, said, no. Everything's made of 4 elements, earth, air, fire, and water. Like almost all of his physics, Aristotle was completely wrong. But nonetheless, he had a good agent or something. And so, as a consequence, for the next 2,000 years, the idea of atoms had been banished from the discussion in the Western world. But in the 18th century, it was resurrected as an idea. And as of 100 years ago, and this is the United Nations Year of Quantum Science and Technology, it was exactly 100 years ago this year, that we developed a model of remarkable precision that describes the way atoms work in the world. This model is called quantum mechanics, and we're not going to talk about that tonight, unless you have deep questions about it. But nonetheless, it's by far the most precise model in any field of science that has ever been developed. The model makes predictions to 10 decimal places, and experiments confirm those predictions. But the particles that make up the coffee and the ceramic and the silver and stuff are what we call molecules. Now I say there's 4 states of matter here, solid, liquid, and gas. I only put 3 up there. The other state is the plasma. It's what 98% of the universe is made of, but we don't have that on Earth, because that happens at temperatures of 5,000 to 10,000 degrees and above. Unfortunately, even with global warming, we don't get that hot here. But molecules, there's millions of molecules. Naturally occurring molecules, molecules that we make in labs. But there's millions of molecules, and what a molecule is a precise recipe of smaller building blocks that we call atoms. So the water molecule, you know, consists of 2 hydrogen atoms and 1 oxygen atom. But the water, the smallest unit that's water, that behaves like water, is a molecule. These smaller building blocks, which we call atoms, there's only 118 of. And that's a lot smaller than millions. So the enormous variety of materials that make up the universe are a consequence of the combination of atoms from two, like the oxygen you're breathing as you're sitting there is two oxygen atoms stuck together, that's an oxygen molecule, up to 2 billion, which chromosome number 1 in your DNA is a molecule with 2 billion atoms with a precise proportion of each kind. In Greek, atomos means uncuttable, because it was the smallest piece of paper I could get to, and I couldn't make it any smaller. We now know that atoms, which we derived obviously from atomos, are in fact not uncuttable, but they're made of smaller particles called nuclei, which are positively charged, and electrons, which orbit around them. There are about 3,300 kinds of nuclei, even though there's only 118 distinct atoms. And then it turns out that the nuclei are made up of two smaller particles called protons and neutrons. And the protons and neutrons are made up of triplets of smaller still particles called quarks. And I don't know if the Russian dolls get smaller than this or not. But for the last 100 years or so, we're stuck at this level, and we have a highly predictive, precise, and informative model. What we're going to talk about tonight, we don't need to worry about the quarks and the weird particles like intermediate vector boson. We just need to worry about atoms and their nuclei. And they will provide the key to reconstructing history. So an atom, as you've seen in the textbook, undoubtedly you remember from your high school chemistry teacher, a traumatic experience, no doubt, had this thing in the middle called the nucleus with protons that are positive and neutrons that are neutral, and orbiting around on the outside are electrons. There are two numbers that describe every atom. One is the atomic number, which is the number of protons. When I say there are 118 atoms, there are atoms with 1 proton, with 2 protons, with 3 protons, with 4, up to 118. Couldn't be simpler. Number of neutrons is variable, however. And so we have another number for the atom, which is the atomic mass. It's not a mass in pounds or kilograms, but it's a mass that's equal to the number of protons plus the number of neutrons. So it's just a number, you just count them up. And so carbon, the atom on which life is based, has 6 protons. If it has 6 protons, it's carbon. If it's carbon, it has 6 protons. And in this instance, at least, it has 6 neutrons, so we call this carbon-12. Now, the problem with this picture is that it's grossly misleading. Because if the tennis ball is the size of the nucleus there, then the electrons are orbiting through New Jersey and the South Bronx, if I put the tennis ball outside my office on 120th and Broadway. So when I say the atom is mostly nothing, that's what I mean. There's a tennis ball sitting on the corner of 120th and Broadway, and there's an electron somewhere in New Jersey and another one somewhere in the Bronx, and then there's some beyond that as well, in Pennsylvania and out in Long Island. So the atom is 99.99999999999% empty space. Now, the arrangement of those electrons, however, is critical, because it's the electrons, it's the outer messengers of the atom that determine how the atom interacts with other atoms and joins together to form things like molecules, which make up everything around us. And it also determines how they interact with light. Light, for my purposes tonight at least, comes in little packages called photons. And the distance that the electrons can orbit from the nucleus of an atom are exactly specified. They're different for each atom, but the distances are specified for each atom. And as a consequence, the electron is bound in the nucleus with a certain amount of energy. And it can jump between levels, but it cannot exist. It's just not that it doesn't hang out there. It cannot exist at a place in between the various orbits it has. And so, therefore, since jumping orbits takes energy, jumping up absorbs energy, jumping down gives off energy, the photons, the energy of the photons with which the atom interacts, tells you what the atom is, because each atom has a unique signature. So say we have a star shining light of all the colors of the spectrum, but there are some atoms in the atmosphere which absorb at particular wavelengths, which correspond to particular colors, and therefore we don't see them, so there's black lines in the spectrum. So here's an actual spectrum of the sun. So these lines go next to each other, so they'd be to Watermill and whatever, the Hamptons over there. If you spread them all out, and you see there are thousands of these little black lines. Each element has a unique signature, unchangeable, unique signature, where dozens of these lines belong to each kind of atom, which of course is the way we know what the universe is made of, the way we know the remarkable fact that the universe is made of exactly everything the Earth is made of, because exactly those same atoms appear in every star and galaxy we observe. One more thing we need to know before we get to the historical stuff, and that's isotopes. I said the atoms exist with 1 proton, 2 protons, 3 protons, 4 protons, 5 protons, but they have variable numbers of neutrons. Protons are positively charged. Like charges repel each other. So you pack a bunch of positive charges together, you'd expect they come flying apart, because they repel strongly, and the closer you put them together, the more strongly they repel. So you need extra glue. The protons have this other force they respond to, unimaginatively called the strong force. But the neutrons, which are neutral and therefore don't contribute to the repulsive force at all, also add glue, add strong force. And so adding neutrons helps stabilize the nucleus. So I said before that carbon has 6 protons always, but it also has 6 neutrons in some cases. In other cases, it has 7 neutrons. And so that makes it carbon 13. 6 plus 7 is 13. And carbon sometimes has 8 neutrons. So that's 6 protons, because it's carbon, plus 8 neutrons is carbon 14. Likewise, hydrogen can either have 0 protons, or 1 proton, or 2 protons. This doesn't change the way the atom interacts with the outside world. It doesn't change chemistry at all, because those electrons are in New Jersey and the South Bronx. They don't know what the hell's going on in the nucleus of the atom. But it changes the mass of the atom, because the neutrons and protons both have mass. And it changes the stability of the nucleus of the atom, because the correct ratio of protons to neutrons is essential. So for example, in carbon, I say there's carbon 12, carbon 13, and carbon 14. And these will be critical in much of what I talk about, so that's why I spent a moment on it here. If you take your fingernail, it's got a lot of carbon in it, 99 out of 100 atoms are carbon 12, 1 is carbon 13, and 0.00001 in a trillion is carbon 14. You might think, well, don't have any carbon 14 in my fingernail because it's only 1 in a trillion. Remember, atoms are very small. There are 10 billion carbon 14 atoms in your fingernail, even though they represent only 1 in a trillion of the carbon atoms that are there. Now, it turns out that carbon 14 is special because it has a mismatched number of neutrons to protons. 6 and 6 is really stable. 6 and 7 is good enough. 6 and 8 is just too many neutrons. And so it spontaneously undergoes a transformation from carbon to nitrogen. You see, you still have 14 protons and neutrons, but one of the neutrons changes into a proton, and now we have 7 and 7, which is a good stable ratio. Forget the other particles that come up. Not so important. But this gives us a clock. For the light elements, so this is number of protons versus number of neutrons, for the light elements like hydrogen, helium, and carbon, nitrogen, and oxygen, equal numbers is what we want. But as we go to heavier and heavier elements, with more and more of those positively charged repelling particles in the nucleus, we need extra glue, until we get up to uranium, where we need something like 148 neutrons for every 92 protons, just to keep the nucleus from falling apart. So every single element, that's number 1 through 118, has a variety of so-called isotopes, iso meaning the same, so with the same place in the periodic table. And the ratio determines whether they're stable or whether they're unstable, and how they fall apart. And they fall apart in a completely random way. Now this is still a controversial idea. It's an idea that Einstein utterly rejected and spent the last 40 years of his life trying to disprove. But as far as we can tell, it is absolutely correct. If I have a carbon 14 atom, and I sit it on my desk, it might decay in the next 3 seconds. It might not decay for 30,000 years. If I have, on the other hand, 1,000 carbon 14 atoms, I can tell you precisely how long it will be before I have 500 left. 5,730 years. Half of them will decay in that time. And then you may think, well, so at 11,460 years, I'll have none left. No, 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 no. The atoms don't have a memory. They don't know when you started looking at them. They don't know how long they've been around. They randomly decay. And so in another 5,730 years, half of the half are gone, so we're down to a quarter. And then half of that is down to an 8, and half of that is down to a 16. When I have my students do this, I have them all stand up and flip a coin. At least I used to. They don't know how to flip coins. I guess because they don't use coins. I don't know. They have no clue how to flip a coin, so it's a total disaster. But anyway, if you're flipping coins, which is a purely random process, right, half of you, if all of you stood up, you flip a coin, if its tail sat down, half of you would sit down. If the one still standing flipped again, half of you get heads and half of you get tails. Right? That's what it is, 50-50. So half of you would sit down, you have a quarter of people left. That's the way radioactive decay works. And what's remarkable about it is it's an imperturbable clock. You can take a radioactive nucleus, you can dump acid on it, you can heat it to 1 billion degrees, you can cool it to 0 on the absolute temperature scale, you can hit it with a hammer, you can do anything you want to, and you cannot change its inherent probability of decaying such that half of them will be gone in one half-life. So, how do we use these things? The Shroud of Turin. Anybody know what the Shroud of Turin is? The punitive burial cloth of Christ. It's in this silver casket in the cathedral in Turin. It used to be in France. And there was great controversy over this. It's a cloth here. You see the image of a person here. The radiant Christ arisen. How old is this cloth? Well, we can use carbon to find out. Because this cloth is made of linen, and linen comes from flax. And flax is a plant. What plants do is they suck carbon dioxide out of the air, that's CO2. They use sunlight to break the bond between the O2 and the carbon. They breathe the O2 back into the air, which is nice for us because that's what we breathe in. And the carbon goes into making up the cellulose or the fructose or whatever the plant material needs. And so, as the carbon is breathed in from the air, most of it's carbon-12 O2, because 99% of carbon is carbon-12. 1% is carbon-13 O2. But 1 part in a trillion is carbon-14 O2. And as it breathes in, the carbon-14, because it's chemically identical, just gets put in the little chain of carbon atoms that make up the cellulose or whatever it's involved. However, once the plant dies, or once you harvest the flax, it stops breathing in carbon dioxide, right? It's dead. The carbon-12 is still there. The carbon-13 is still there. The carbon-14 is decaying away. And so, you can calculate the number of carbon-14s that are left, you know how many you started with, and you can figure out how old it is. So for example, on this exponential curve here, if that cloth were produced in 1350 AD, and I'll show you why I picked that date in a minute, you would have 84.9% of the carbon-14 left. Whereas if it were in 30 AD, actually the burial shroud of Christ, then you'd expect it only had 0.785 of the carbon-14. Now, those two numbers may not look too different to you, but we can measure this to 5 decimal places. Those are radically different numbers. So all we need is a few millimeters of this cloth to count, literally count atom by atom, the number of carbon-12s, the number of carbon-13s, and the number of carbon-14s. Take the ratio, and we've got the answer. Now, in this case, it took 30 years to convince the Catholic Church to give us a few square millimeters of this cloth. But, in fact, it was just verifying what we already knew. Because there is a letter to the Avignon Pope from a bishop in France that says, the case, Holy Father, stands thus. Sometime since the dean of a certain collegiate church, Leary, falsely and deceitfully being consumed with the passion of avarice, and not from any motive of devotion, but only of gain, procured for his church a certain cloth, cunningly painted, the truth being attested by the artist who had painted it, to wit that it was a work of human skill and not miraculous insight. Pilgrims made, in the Dark Ages, made lots of pilgrimages to places where you had a bone of St. John or whatever. And this was the burial cloth of Christ. So the guy made a fortune. But, in fact, it turns out the flax lived 1325 plus or minus 65 years ago. So obviously, that confirms this conclusion. We can do better than that, and we can do better not just by destroying a little piece of the cloth, but just by inquiring of what atoms exist in paintings. This is the betrothal of St. Ursula. In 1930, the Metropolitan Museum of Art was offered this for 30,000 British pounds, which would be $600,000 in today's money. Now, it was the first few months of the Great Depression, and $600,000, I guess, was a lot even for the Metropolitan Museum. So despite the fact that this had been verified as a 15th century painting by the Spanish maestro Jorge Enriquez, by the head of the British Portrait Gallery and a number of other art experts in Europe, the man was still a little suspicious. So they went 50 blocks south to the Morgan Library, where there is a remarkable woman named Bella da Costa Green, who pronounced this a fake. And the reason she pronounced it a fake is because over the previous 25 years, and she was the librarian there for nearly 50 years, for the previous 25 years, she'd acquired half a dozen of these fakes. In fact, she had already dubbed him the Spanish forger. I say him, we don't know, it was a he, it could have been a she. And they were painted in Paris around 1900. And there were 350 of them that have already been found. In fact, there were big museums in the world that have exhibits just of the forgeries of this one person. Now, very clever. They're all on wood, or on vellum, or on parchment, and it's all medieval wood, parchment, and vellum. That is, the carbon-14 dating says that it's 550 years old. But how do we tell what's actually in the painting? Well, we could come and scrape off some of this green stuff here, but that would be sort of sad if it really were a 500-year-old painting. So we do something much cleverer. We probe the atoms that are in there to see what atoms make up the pigments of the painting. Do, for example, the green leaves around the border, which look exactly the same color as the green leaves inside in the trees, are they the same? We use autoradiography. We take this painting, we put it next to the nuclear reactor in Brookhaven, and irradiate it with neutrons. Billion neutrons per square centimeter per second. And I think, God, you must melt the painting, you must destroy it. Remember, there's the tennis ball at 120th Street, and the electrons are in New Jersey in the South Bronx. You can throw a lot of tennis balls and not hit anything. So 99.99999% go right through. But occasionally, one of the neutrons gets stuck by hitting the nucleus of the atom, by actually hitting the tennis ball head on. And a few nuclei, I mean like 5, are transformed. So what happens? You have this big nucleus, let's say thorium-233, number 90 in the periodic table. You add a neutron, it gets stuck, so it's now thorium-234, still number 90. But that's a bad ratio of protons to neutrons. And so it undergoes a decay where it spits out an electron and creates number 91 in the periodic table, palladium. And it's excited because it just got all screwed up because the electron was flying out of the nucleus. And so it deescites and emits a gamma ray, which has a unique energy only to palladium-234. And as a consequence, you can tell that that painting had thorium-233 in it without touching the painting. So what do? You radiate the painting, a few nuclei are transformed, you then put a piece of film, some of you look old enough to remember what film is, our students don't do that. And you record where the electrons come flying off, so you know exactly where the different pigments are. And then you use an X-ray detector to determine what the signature energies, the colors of the X-rays are, so you know exactly which element it is. And so, when, for example, you scrape, you don't have to scrape the little green paint off, you just irradiate it with neutrons, you find that it's arsenic, copper, and oxygen, a pigment that was invented in 1814, clearly not from the 16th century. That is an interesting story about Paris green. It was invented in 1814. It was Napoleon's favorite color. And so when he got exiled to St. Helena in the South Atlantic, he had his entire rooms painted with this color. He also died of arsenic poisoning. All right. What about this? This is not a forgery. This is a real painting. Some of you have probably seen it in the Metropolitan Museum, the St. Rosalie interceding for the plague-stricken of Palermo. It's by Anthony van Dyck, 1624. But what can we learn about this painting? Well, we want to know what pigments he used. And so let's look at the light brown cloth over the umber robe here. And let's look at these pieces of the sky which are down below. So what you do is you irradiate the painting, and then you put film on for a few minutes, then a few tens of minutes, and then a few hours, then a few more hours, then a day, then a couple days, then a week, then a couple weeks, and then a year. And you see which radioactive decay elements are producing energy in different parts of the painting. In the meantime, you put on the gamma ray detectors to determine which elements they are. And so, for example, umber and dark ochre have manganese 56. This one has copper and sodium, and bone black has phosphorus. So we irradiate them with neutrons. We get them excited. They decay. So here's the painting in black and white. Here you see the brown cloth, completely different color than the umber of her robes. And that's because the manganese 55 has become manganese 56, which has a 2.5-hour half-life. So after a few hours, it's still decaying away. And we know that's where that paint came from. Whereas here the cloth is a brighter color because it's got a little bit of copper, carbon, and oxygen in it. The copper went from copper 63 to copper 64, 12-hour half-life. After a day, it's still decaying. And ultramarine down here, sodium 24, a 15-hour half-life. So these are dark, exposing the film. But then if you keep it on for 8 to 20 days, this is what you see. And if you flip this upside down, you see it's a lovely self-portrait of Van Dyck that exists underneath the painting of St. Rosalie's. My wife is an artist, and she does this all the time. She paints on something, doesn't like it, so she just paints over the top of it. So if you had eyes like the autoradiographer, when you enter the Metropolitan Museum, you get to see 2 paintings by Van Dyck by just looking at one. Here is the greatest modern forger of all time, Wolfgang Beltracchi. He painted, didn't copy paintings and try to fake them. He made up new paintings by the expressionists and surrealists of the first decade or two of the 20th century, Leger and Campendonk and other people. And he sold them for a total of $100 million before anyone noticed that they weren't real. He had a great story. His wife, who was an accomplice in this, said that her grandfather had purchased all these paintings in 1910, 1915, and then when the Nazis came to power, he hid them in a cave outside of Cologne so the Nazis wouldn't get them and destroy them. And they went so far as to rent a house, hang these paintings in the house, dress up Helen, the wife, as the grandmother in period clothing, and take pictures so you could see these paintings really were hanging on the wall in 1910, when of course they'd just been painted in this guy's studio in 1990. Many famous people bought these paintings at famous auction houses in Europe and in New York. And it wasn't until one sold for $2.5 million that a clever collector decided it should be inquired of. And so again, rather than firing neutrons, he fired protons at the painting. That excites the electrons in the atom. They de-excite by emitting the specific signature color photons. And indeed, it was shown that the titanium white that was used was invented just 2 years after the dating of the painting, of the fake painting had been made. So if he just missed by 2 years, he really could. Anyway, $100 million, 100 million euros rather, was not bad because he only got a sentence of 6 years in prison and in fact served less than 3 years. And had to give a few $1 million back. So he's still extant and living the good life from his work. All right, those are things we know from written records and from direct observation. But these, of course, are the origin of art, the cave paintings in France. These are done with charcoal. What is charcoal? Charcoal is burnt wood. What is wood? Well, wood used to be alive. That means it was sucking carbon dioxide from the air, including carbon-14 and carbon-12. If you take the ratio, you can figure out how old these are. And in fact, these range from 30,000 to 32,000 years before the present. Now, Europeans, of course, regard themselves as the center of all art, and clearly they were the first to invent this. Until a few years ago, these drawings were found in a cave in Sulawesi in Indonesia. And you see this is a nice wild boar here. And here's a bunch of handprints. Imagine this one's in a daycare center or something. The problem with this is it's not charcoal. It's mineral, it's iron oxide. And so it was never alive. So there's no carbon in it, so you can't do carbon dating. So how are we going to figure out how old this is? Well, we use what are called speleotherms. Speleotherms are stalagmites and stalactites. So if you've been in a cave and seen these calcium carbonate-rich drips and really build up from the floor and down from the ceiling. Well, if you look on here, you see there's these little deposits over the top of the drawing. So the drawing must be older than those deposits. How do we figure out what those deposits are? Well, it turns out this water laden with minerals has lots of uranium and no thorium. But conveniently for us, uranium undergoes a decay to thorium. So if we take the ratio of uranium to thorium, we can tell how old it is. And these are, in fact, 40,000 years old. They're 10,000 years older than the cave paintings in France. Now, of course, Europeans might or might not acknowledge this, but at least we know that Homo sapiens invented art, except maybe not, because this is a Neanderthal handprint. And while somewhat controversial, it looks pretty much like a hand to me. And it's more than 65,000 years old. You are what you eat. So I said you're made of atoms. And every single atom in your body is something you ate or drank or breathed in, with the exception of a few in your tooth enamel, which may have been donated by your mother. But the atoms in your body turn over all the time. So some of them in your skin turns over on timescales of weeks, in your bones on timescales of decades. But human diet reflects the ratios of isotopes of different atoms that you breathe in, that you eat and breathe in. And in particular, this is useful for certain kinds of plants. So, there are two routes of photosynthesis. One involved 550 million years ago when plants came onto land for the first time and are called C3 plants. And what they do is they grab the CO2 out of the air, that's what plants do. They split out the O2, breathe it out, take the C, and they make a chain of 3 carbon atoms in a row. That's the first thing, and then there's a more complicated step to photosynthesis. About 25 million years ago, so recently in evolutionary timescale, a new mode of photosynthesis developed in response to the changing climate, such that they grab CO2 out of the air, split out the O2, breathe it out, but they have to have 4 carbons in a row before they can make the next step. Now, think of carbon-13, not radioactive, carbon-13 and carbon-12. The only difference between carbon-13 and carbon-12 is that carbon-13 is more massive. I run 6 New York City marathons. I can't do that now. I'm more massive, and therefore I move slower. So more massive things with the same amount of energy move more slowly. The C3 plants are really impatient. They want bang, bang, bang. They want 3 carbons in a row, and they suck in the C12s and discriminate against the C13. The C4 plants also discriminate C14 because C13 because it's moving slowly, but they have to be a little more patient because they have to wait for 4 carbons in a row. And so when you end up with the plant material, you find that compared to the air, the C13 to C12 ratio in C3 plants is 2.85% low, and in C4 plants it's only 1.25% low. Now you are what you eat. And in particular, it turns out that while most things that grow in temperate climates are C3 plants, maize, that's corn, sugarcane, and sorghum are C4 plants. Maize was developed about 8,000 to 9,000 years ago in the highlands south of Mexico City from a plant called teosinte, which has like 3 kernels, so you would not recognize an ear of island corn, teosinte. But back 8,000, 9,000 years ago, the native indigenous people learned how to crossbreed the plants that had 4 kernels instead of 3 kernels, and eventually developed corn. Corn is a C4 plant. So you might wonder how corn got from the highlands of Mexico, south of Mexico City, to New England when the Pilgrims showed up in 1620. And the answer is you can trace that precisely by looking at the bones of indigenous people over time. If you go, for example, to Ohio and dig up these bones, you get the date from the C14, and you get the fraction of their diet that was corn from the C13 to C12 ratio. That fraction is 0% because all temperate plants are C3 plants, until about 1,250 years ago, when in the space of a century, their diet went from 0% corn to 70% corn. And of course, it wasn't just their diet. The chickens ate the corn, and the deer ate the corn, and they ate the deer. And so the isotope ratios of carbon-13 to carbon-12 can show you, tracking across the country, exactly how corn agriculture spread up until a couple thousand years ago when you find it in New York State. This has lots of medical applications and diagnostic applications, as well as archaeological applications. And then one of my favorite stories, the mammoth. So here's a woolly mammoth. This woolly mammoth has big tusks, 3 meters long. Lived 17,100 years ago. And what they did, because this tusk grows continuously over time, and the tusk reflects the elements that the animal ate, they took samples, several 100,000 samples along this tusk, such that they had a weekly measure, every week over this animal's lifetime, of what isotopes it was eating based on the plants that was eating and the soil it was growing. And in particular, the strontium-87 to strontium-86 ratio tells us a lot about this animal. So here we have strontium-87 to strontium-86. We see it was born and it hung out with its mother for a long time. At about 16 years, the character of its annual migrations radically changes. 16 years is the time at which young males leave the matrilineal herd in Africa today for elephants. Here we have carbon, here we have oxygen 18, and here we have nitrogen. We can plot from the strontium ratios where the animal was in Alaska every week of its life for its entire 28 years. And we can tell exactly how it died because up here you see a huge spike in the nitrogen 15 to nitrogen 14 ratio. You bring in nitrogen in the food that you eat, you excrete nitrogen 14 a little better than you excrete nitrogen 15 just because it's lighter, so it moves faster, so it goes out in your pee faster. But nitrogen 15 gets incorporated into your proteins. If you stop eating, you have to start digesting your own proteins. And so the nitrogen 15 goes up enormously. This elephant, this mammoth, was born over here, and you see this black line? That's where it was every week of its life for 28 years, 17,000 years ago. And it died up here when it got caught north of the Brooks Range and clearly ran out of food, particularly during winter. Being able to reconstruct stories like this is quite wonderful. And it's even relevant to other problems we face today, like Earth's climate. Because trees are what they eat too, right? They're tucking things out of the soil, they're breathing in water and carbon dioxide from the air, and the trees, as you've probably seen if you've seen a tree cut down, have rings that grow annually. Leonardo da Vinci, and many things, was one of the first people to recognize that we could read the past seasons in the rings of trees. And indeed we can. So a big fat ring means a good year, a long growing season, plentiful water. A little skinny ring means it was a tough year, no drought or not much water. And a short growing season, see it starts out with big rings and slows down later in life. But this goes back as an annual record, unambiguous, because you have to count from the outside in, for, in the case of these bristlecone pines, if you're ever on the border of New York, of Nevada and California in the White Mountains, I recommend visiting this place. It's really eerie. These look like sort of cartoon old trees, right? They're 5,000 years old. So we have a continuous record for 5,000 years, and we don't have to cut them down. We can measure the width of the rings for 5,000 years and record the history of the climate at this location. And we don't just look at whether the ring is fat or skinny anymore, because now we've got these isotope ratios. So oxygen 18 with H2O is heavier than oxygen 16 in H2O. And so oxygen 18 means it has to be warmer to evaporate into the atmosphere and then fall down in California as rain. And so the O18 to O16 ratio gives us a temperature accurate to 1/10 of a degree centigrade. And the C13 to C12 ratio, for reasons I won't go into, gives you the humidity. So we can reconstruct the temperature record at any given place. And so we've done this for trees in Northern Europe. And this is the last 2,000 years, simple. And you see plus or minus 0.2 of a degree centigrade. It bounces around a little bit. But about 500 AD, it starts to rise and it stays warm up to 0.6 of a degree above average in what's called the medieval warm period. The weather was actually pretty good in the medieval warm period. And unsurprisingly, this is when the Vikings went to Greenland. If you've ever flown over Greenland, you might wonder why they called it Greenland, because it's pure white, right? But that's not true in the medieval warm period. Here's a barn, they had a cathedral, they had a homestead. There were several thousand people living there. They brought their sheep and the cows with them. They also ate seals. They hunted walrus. It turns out walrus ivory was a huge commodity in medieval Europe. And in 1021 AD, 1,004 years ago, they went off to visit Newfoundland. And this is the place in Newfoundland that Leif Erikson took his merry band of people, it turns out, because there were lots of knitting and weaving instruments, so probably it was women as well as men. So there's 1021 at the peak of this warm period. But then it started to get colder. And when it gets colder, it means the growing season is shorter, it means you can grow less grass to keep the hay for your crops, for your animals during the wintertime. And by 1450, the Greenland colony had disappeared. And then it kept getting colder, down into this period here where it's now 6/10 of a degree below the average, which is called the Little Ice Age. And it's not a surprise that the period when the mass migration from Europe in 16 and 1700s to the United States happened because times were really tough. It was really cold. There are pictures like this from the early 17th century Dutch paintings. The canal's never been anymore. There's a famous race in the Netherlands. They haven't been able to hold it for 45 years because it never freezes anymore. But in medieval, in this Little Ice Age, it did. And I should note, that's where we are today. So you see what's happened over the last 2,000 years. But we have this continuous record going back 13,900 years from trees that are buried in mud and preserved, that are used in ancient buildings, that are preserved in peat bogs. And we have a continuous annual record going back 13,900 years for the temperature and the humidity. I'm going to skip this because it's a little great. But that's still relatively modern history. Let's go really deep and go to the death of the dinosaurs. So it turns out that it was known in the middle of the 19th century. There was a sudden change in the character of the fossils that were below a particular strata in the land and above the particular strata. And this is now called the Cretaceous-Paleocene boundary. And you see it here in Italy. It's a very striking layer of gray clay kind of stuff. Below this, you find dinosaur bones. Above this, you never find dinosaur bones. This was a mystery from the middle of the 19th century up until 1980, when a young geologist, just leaving his postdoc at Columbia and going to the University of California at Berkeley, recognized that while all the elements were the same below and above this transition, one element, iridium-193, very heavy element, none of which exists on the surface of the Earth except that which rains in from outer space, went up by a factor of 30 or 25 or so, right at that boundary. A huge increase, whereas the typical increases were 1%, 2%. This is 3,000%. And indeed, the conclusion is that that came from space. I remember vividly the colloquium given by this geologist's father, Louis Alvarez, at Columbia, where all the Nobel laureates are lined up in the front row for the colloquia, and they're ready to dump crap on people, right, because they're smarter than everybody else. And Louis Alvarez, who's also a Nobel laureate, got up and gave this hypothesis that the dinosaurs were killed by an asteroid from space. And there's people walked out shaking their heads. Isn't it sad when old people, lose it? I thought it was a brilliant hypothesis, and it turns out that it's totally correct. You can date these things using zircons. We take the amount of uranium that's left and the amount of daughter product that's left. We just have to read off this diagram. So this is the exponential decay of the parent. This is the exponential rise of the daughter. If it's right there, then it's 2.3 half-lives ago. And so it turns out we know this date to 5 decimal places. It would be like me looking at you and being able to tell within a week when you were born. 66.043 plus or minus 0.04 million years ago. We know what happened asteroid struck the Yucatan Peninsula in Mexico. It ignited all the forests on Earth. The entire Earth went up in flames. There were tsunamis 1/2 kilometer tall. There was anhydrite. Unfortunately, the dinosaurs really didn't luck out because this place where it hit in Mexico is rich in sulfur. Sulfur, when it gets thrown high in the atmosphere, becomes sulfuric acid droplets and reflects sunlight. And so the temperature fell from about 20 degrees centigrade to -5 degrees centigrade in a matter of a week. And if you have to eat 1/2 a ton of stuff a day to keep your brontosaurus stomach full, you don't live very long. In fact, all that sulfuric acid in the atmosphere ultimately had to come down, and over the course of a decade or so it did in acid rain, such that we can see a change in the strontium-87 to strontium-86 ratio of the entire ocean at this moment, when the sulfuric acid, roughly estimated as 3 gallons per square meter, hits the rocks on Earth and dissolves the rocks and washes them into the ocean, raising the ratio of those two isotopes. 80% of all marine organisms died, 57% of all plant species died. But little furry things did really well because they stored up nuts for the winter, and that's where we come from. We wouldn't be here were it not for this asteroid. Now we can go back even further than that and talk about the age of the solar system. We use rubidium-87, which has a very long half-life of 49 billion years. That's 10 times the age of the Earth, but it's still decaying. We use it in a very clever way to make it take a ratio of rubidium to strontium, and I won't bore you with the algebra, but all you have to do is plot the rubidium-87 to strontium-86 versus strontium-87 to strontium-86. You get a straight line, and the slope of that line gives you the age of the Earth at 4.568 billion years, again in 4 decimal places. And let's go back to the beginning of time itself, the beginning of the universe. We know the ratio of heavy hydrogen, hydrogen with a neutron, deuterium, to regular hydrogen is about 3.597 - 5. We know the ratio of helium to hydrogen. This tells us what the conditions were like in the first 3 minutes, yes, 3 minutes on your watch, of the universe. It tells us the helium-hydrogen ratio at 300 seconds, the deuterium-hydrogen ratio at 1 second, and allows us to extrapolate backwards in time to 1/1000th of a second of the universe, using just standard physics that we know and love. To calculate the age of the universe is 13.81 billion. So I've gone over a lot of time periods, but let's, like with the poppy seeds. Did they get to the back row, by the way? Get the poppy seed? Let's show what our time on this earth, pondering such questions, means by compressing the life of the universe into a year. So you go to Times Square, you see the ball start to fall 30 seconds before midnight, hits the bottom at midnight. Hydrogen and helium nuclei are instantaneously formed. They form in seconds on the real-time scale, so tens of nanoseconds on this time scale. The first atoms formed 15 minutes later. You have to get your second glass of champagne. And our Milky Way galaxy, by early February, is getting organized with a lot of stars and gas, 300 billion of them or so. And stars are born and stars die, and stars are born and stars die. And at about 10:30 p.m. on September 1st, the sun forms. Many generations of stars before this. And the Earth forms an hour or two later. Within less than 3 weeks, before the end of September, life is flourishing on Earth to the extent that it leaves the fossil record. And then life continues to evolve, mostly in a single-celled form. But by December 15th, the Earth has a little catastrophe. It goes into a snowball phase where almost the entire Earth is covered with ice. Maybe the equator has a few spots and a few volcanoes sticking through. But December 15th, it's a snowball Earth. But the next day, it all warms up again, and we get the Cambrian explosion. Life moves out of the ocean onto land, multicellular life flourishes. And life continues to evolve until Christmas Eve at 10:45 in the morning, the dinosaurs appear. These are these ancient things, right? They appear in the last week of the year. And December 30th at 5:11, and we know that very precisely because I just dated the time of the asteroid collision, the asteroid wipes them out on the next to the last day of the year. So on December 31st, these small furry creatures that survived the apocalypse continue to evolve over the last day. And at 8:50 p.m. on New Year's Eve, when you're already dressed to go to the party, a species diverges from chimps. And over the next 3 hours, it gets more upright, brains grow bigger, its jaw changes. And 11:49:25, that is with 10 minutes and 35 seconds left, Homo sapiens appear in the modern form. With 1.10 seconds left, the cave paintings in France are done. With 30 seconds left, the ball begins to drop in Times Square. With 29 seconds left, the mile of ice that was just across the Sound here and left the glacial till that is Long Island that you're sitting on starts to recede. Pyramids are built with 9.5 seconds to go. Roman Colosseum with 4.4 seconds to go. Chichen Itza in Central America blossoms with 2.5 seconds to go. Then Columbus discovers and quotes the New World. The ancient form of democracy in the United States is 55/100ths of a second old. You were born, I'm being generous to some of you, with 1800ths of a second to go. I was born, that's supposed to be I was born with 1800ths. You were born with 900ths of a second to go. And I began this lecture less than 1 microsecond ago. It's now midnight. Thanks to you.
Did I hear you say that we wouldn't be here if the dinosaurs didn't die?
That's likely the case. Mammals did exist with the dinosaurs over the last 10 or 15 million years of their reign, but they were clearly dominant in the ecosystem, and it's really unlikely that these furry little moles would have developed the speciation that we've developed. Dinosaurs were around, after all, for 250 million years, so this is a short period of time since then. And in that 250 million years, no other species came to dominate the ecosystem.
You very quickly described how you came to the 13.5 billion years of the age of the universe. And I'm sure it's very complicated as to how that calculation was made, but essentially the question is, if by universe you mean everything that we're aware of that exists anywhere, how do they possibly come to that kind of a dating process?
Well, so first of all, it's important to recognize the universe means space and time, not just stuff. So the space and time of the current universe was created 13.8 billion years ago. And don't ask me what was before that, because there's no before when there's no time, and there's no where when there's no space.
So there's the Big Bang.
So the Big Bang happens. And yes, that I did not obviously tell you the details of how it's done, but we have 2 or 3 independent ways of doing this. Mostly actually by looking at the radiation that we can see from when the universe was 390,000 years old. It was the first light from the universe we can actually see. We can measure with great precision and how it varies on the sky. And our model then fits the 13.8 world.
Is there a theory as to what caused the warming period that was about 1,000 years ago?
So that's an interesting question. So first of all, note that that was in Europe, Northern Europe, as a matter of fact. And it's not known, actually, whether that was a global phenomenon or not. So we don't yet at least need a global theory when that's true. There are systemic changes in the ocean currents. So right now, the whole ocean, the entire world's oceans are driven by the fact that the Gulf Stream comes up the east coast of the United States, goes over to Europe, keeps Europe much warmer than it would otherwise be, gradually cools off, and because the Atlantic is saltier than the Pacific, salty water is dense, cold water is dense, it sinks to the bottom of the ocean, runs all the way down to Antarctica, out into the Indian Ocean and the Pacific. The entire global circulation is driven by that. Small changes, relatively small changes on that, can lead to temperature changes. And so there's now suspicion that indeed that current is slowing. And if it slows, as a consequence of global warming, England and Germany and Norway are going to get cold. They're going to get colder because they won't have that warm water supply. So it's not it's a global phenomenon, but the effects of it are different in different places.
The current models of artificial intelligence or machine learning, can they contribute to this type of modeling and carbon dating?
I am an AI virgin and hope to remain that way. I think, certainly not directly. When we measure the isotope ratios, which are key to most of what I talked about, we literally take the substance, we vaporize it, we throw it through a magnetic field, and we have little buckets, and the carbon 12 goes in this bucket, and the carbon 13 goes in this bucket, and the carbon 14 goes in that bucket, and the radium 87 goes in that bucket, and we literally count the number of atoms. So it's not hard. It's like that 6-year-old can do it. You need a little equipment, but it's literally counting, and then taking the ratio and fitting it to the exponential curve that represents radioactive decay. Things like, where did the 6/10 of a degree come from in the medieval warming period? You need a very complex model of the Earth's ocean and atmosphere system, and that people are applying AI tools to do. But that's a why question, not a what question. Yes?
If you change anything after that warming period on Earth, could be caused by the absence of solar activity from Mars or Anima?
Yeah, so the question was, can these things be modulated by solar activity? The sun has an 11-year sunspot cycle, where it's active and inactive, 11-year time scale, or near just past the most active point right now. And we see evidence of that in the isotope pressure. Because when the sun is active, it produces carbon-14, and when it's less active, it produces less carbon-14, as well as things like beryllium and things like that. So the solar activity certainly changes on timescales of decades. Whether the solar activity changes on timescales of thousands of years, not at all impossible. We just don't have records going back that far. We have records of stars, and we have stars like the sun. We don't have to look at the sun. Stars like the sun all show these cycles of decades, a couple decades, 3 decades of activity. But we only have 100 years worth of data, so we can't say whether on 1,000-year timescales they have systematic modulation. But it doesn't take much. It takes the difference of a few tenths of a percent to warm or cool because of solar activity. So solar activity is certainly one possible explanation. Okay. Well, as was indicated, there is a book. It gives much more detail, but at no more complex a level. And if you're slightly depressed about the state of alternative facts in the world, there's another book that I wrote a while ago. And this is the nicest thing anybody said about me. Richard Dawkins' ability to explain our existence with George Carlin's ability to make us laugh. Paul Offit's the guy you hear on the radio all the time talking about vaccines instead of vaccines. Anyway, thank you very much for your attention.